Okay, so let us start. How many of you remember what we did last lecture? There was a gap of 1 week, but do you remember what we covered in the last lecture? Remind me what we did. We were talking about energy based model. In energy based model, how do you train the model? Generally, the usual one, vanilla one, contrastive divergence. What is the issue is with contrastive divergence? You need to sample, right? So we started discussing that can we train energy based model using some scheme, some technique, some way that will not necessitate computing the, I mean, drawing the sample. That was the motivation where we started. And starting from that motivation, we talked about code. What is a code? Stein's code, right? Stein's code function. What is a Stein's code function? It's a vector field. It is the gradient of the log probability. Gradient with respect to x, the random variable, not with respect to theta. Why is code important? Because the normalizing constant is not a function of x. When you take gradient, that vanishes because the problem was normalizing constant. That vanishes, right? But then how can we use code to train our model? Fisher divergence, right? And using Fisher divergence, then we saw that what is the problem with Fisher divergence? There is log probability, gradient of log probability of the actual data, which we do not know. So we did some derivation and arrived at some simplified form which we can actually use. That is all that we did in the last lecture, right? Remember now, right? So today's lecture we are going to continue with the score, right? Uh, and from there we will see that what more can we do with the score. Okay, before that, I think this week and the next week will be the last lecture for this course. Because starting 21st, I am not here, I am returning on 29th when the exam is scheduled. Okay, which means over the next 14 days, 13 days, because Monday I am here, next to next Monday. Over the next 13, 14 days, whatever, including today, there will be 8 lectures. Today, Friday, Saturday, Monday, Tuesday, Friday, Saturday, Monday. So that's the heavy schedule we have starting today. But the idea is that, okay, there might not be 8 lectures. The idea is that there will not be more than 8 lectures. I mean, that is how I should put it, right? And the idea is that in those lectures, we will wrap up this course. So what all we can cover? Obviously, we are starting with something today, which we will see. Um, and the idea is that to cover diffusion and, if possible, flow matching. So these are the two things we will cover. One thing that I said we will probably cover was the GPT, which obviously you can understand that I will not have time for that, right? Because that will itself need 4 lectures for transformer and all of those things. Hopefully, that I will cover next semester. I am teaching deep learning. There I will probably cover that because there anyways I have to cover transformer. So if you know transformer, then it takes next less number of lectures to go from transformer to GPT than from autoregressive to GPT in that sense. Okay. So that is the idea. So there will be a lot of lectures over the next 2 weeks, but then there will be no lectures over the last 1 week. So hopefully you will have time to prepare for the exam. And exam reminds me that it will be 2-hour exam, proper written derivation and all of those things. So practice, solve problems. It will not be MCQ now. Okay. I told it earlier also, but I'm just repeating myself. Okay, let us come back. So we talked about code based model, right? Sorry, code, right? We're talking about code. So we discussed code in the context of, now we discussed it in the context of the energy based model. You have to keep it that in mind. In the context of energy based model. Can someone of you check and tell me what was the Fisher divergence loop that we derived at the end of the last lecture? So we derived it for scalar, right? For scalar, we derived that my f of theta, which is my Fisher divergence, is equal to expectation x drawn from px of x, which is my probability of the PDF of the data, the thing that I want to learn. And then there was one term which was half, if I am not wrong, it was f theta of x whole square, something like that, plus uh, grad x f theta x square of that, no, grad x, hmm, gradients were there. So it was gradient of f, the first term, and the second one was gradient square. Then, yeah, okay. That's why I said remind me. So yes, so it was the first term was half of grad x of f theta x whole square plus the half was missing. So in that case, it will be grad square x, the Hessian, right? Something like this, right? But this we derived with an assumption. What was the assumption? That it was scalar, correct? We derived it with the assumption that it is scalar, right? What will happen if it is vector? How will it look like? I'm not going to derive it, but you should derive it. You never know, that might be a question in the exam. But uh, I'm going to give you the formula. You should derive it. Okay. But it is the same derivation as we did earlier. But I mean, the only thing will be that we did, remember how we derived it? Integration by parts. We will also do integration by parts, but it will be vector calculus. So you have to do over the vector, and that's the only difference. Other than that, it's exactly the same. And when you do over vector, you will get norm, you will get uh, trace, and all of those things. Hessian. Okay. So for vector, it will be f theta is equal to exponential of x p x x half. Now that was gradient of f theta, right? What is gradient of f theta? It is the score. It is the score. Gradient of log of PDF is score. F theta is the log of PDF, so gradient of that is the score, right? So I'm not going to write score now, but I want you to remember that this is the score. So this is norm of and this is kind of straightforward what will happen. I mean, you can imagine it has to be a scalar term. So norm. But the second term is not so obvious. The second term will be trace of the Hessian. If theta square x will give you Hessian, it will be trace of the Hessian. So basically the sum of the diagonal terms. Okay. So go ahead and prove it later, but do prove it. Uh, if you know vector calculus, it will not be difficult. If you don't know vector calculus, some properties you don't remember, then you need to refer vector calculus book. Okay. So this is the generalized score. I mean score, not score. This is a generalized score-based divergence. It's a divergence. And you can imagine that this is what we will use. We will rarely use the first one because we will not work with scalars, we will work with images, we will work with time series, which means we will work with vectors and matrices, which means we will have to use the second one, not the first one. Okay. Okay. And this is what we discussed. This is where we stopped. The first one, right? Now, how does f theta help? Can someone tell me? I told it at the beginning of the lecture today. How does f theta help? No sampling. No sampling. You don't need to sample now. The sampling part has been eliminated. So the advantage is that it eliminates sampling. Everyone agrees? What is the disadvantage? Correct? So advantage is no sampling. Disadvantage is Hessian. Calculation of Hessian is very, very expensive. I mean, you have to do 2 passes of automatic differentiation, and you can imagine that 2 backprop pass for a large network will be very difficult. That matrix will be very large. And then once you calculate that matrix, then you will calculate the trace. You can imagine to do some selective back propagation, but even in that case, it's expensive. I mean, you can imagine if the dimension is D, the pixel size or input dimension is D, you have to at least do D back propagations and then do a sum of that. So D back propagation is expensive. One back propagation itself is expensive, but we are talking about D back propagation. And those D back propagation will happen in per calculation of the loss function or per update of the parameter. So this is expensive. Everyone follows why it is expensive, right? So this is expensive. We will see what we can do about that in a short while. But before that, score based model, right? Or rather, score matching. We called it score matching. We introduced the idea of score matching in the context of energy based model, right? But is it necessary that score matching should only be used for energy based models? Is it not possible that I can use score matching and have a generative model that is not based on energy, that does not have an exponential of minus f theta or plus f theta, whatever you write, but is still a sampling based approach, is still a deep generative model? Because score matching, when you write this score, right, the idea of score is not married to the idea of energy based model. The idea of score is married to that there is a PDF and gradient of the log of that PDF is my score. That is the idea. It is not, we say nothing about energy based model when we define score. And then the Fisher divergence obviously has nothing to do with energy based model. We use it for energy based model. That's probably a use case of this Fisher divergence. But then it should be something even broader, right? Correct. So there is a family of algorithms known as score based model. Score based model for, score based generative models or whatever you want to call it, right? So next we'll talk about score based models, and you will realize very soon, not today, that these score based models are itself diffusion models. So through these score based models, we'll go naturally to diffusion models. Maybe we'll increase the number of steps and all of those things, and it will become diffusion model. Okay, we will see that, but naturally you can understand that it should be quite intuitive that if score is there, and Fisher divergence is there, I should be able to train any network with that, at least in the ideal world, right? Everyone follows this? Correct. So that will become obvious later, not right now. So I'll not go there. Uh, one one advantage will become obvious very soon. Okay. Okay. So that brings us to hmm, no. So the idea, the score based model, the whole idea is that you are avoiding likelihood. I mean, if I'm doing score based model, I should avoid likelihood. So one of the advantage, the disadvantage of likelihood we talked about earlier, obviously that comes naturally. Okay. So let's see. Score based model. Okay. Score based model. The idea of score based models is very simple. And you will see that. But the main ingredient of score based model is a network which I don't think whether it is called code network in the literature or not, but I like to call it score network. The basic ingredient of score based model is a network, neural network, which I will refer as the score network. Okay. So the basic ingredient of, and I'm writing SBM to, I'm too lazy for writing the whole thing. So SBM is core network. What is the score network? Can someone guess? It is a neural network that will take X as input, which is a data, pixels or whatever, and will give you score. Okay. So it's a network where the input is X, X1, X2, X3, whatever. The output is score. Now, if the input is X, which is let's say an image, and output is score, right? Can you tell me if I have D pixels, what will be the dimension of the score? Any idea? What will be the dimension of the score? Score is not a scalar, score is a vector field. The dimension of the score is same as D. When we saw that last time, right? It's if a scalar function, if you're taking derivative of that scalar function with respect to the each of the pixels, the number of pixel will be equal to the number of scores you will get. It's a vector field, which means for this core network, the number of inputs is equal to the number of outputs, right? Because the score dimension, score is what? Gradient of the log of the probability. Probability is a scalar. You will take log of probability is a scalar. You will take derivative of that with respect to each of the pixel or each of the inputs. So the number of inputs will be equal to number of scores, which means for score network, this is a constant. Your number of input and number of output is same. Clear? Okay. We bring this core network into picture. So this core network is theta of x, right? So basically, what does it do? It maps x to s. If I draw a dummy kind of network, that is x1, let's say, x2, x3, and then I have my s theta network, let's say. It's a neural network. It's a very generic kind of neural network. It can have whatever you want, right? And your output is S1, S2, and S3. Obviously, I'm assuming that I have a vector of dimension 3 here. I mean, By no means you need to be restricted to that number 3, but that's just a case we are doing, right? Okay. So, and you can imagine what will happen. Okay. Where S theta is your network. I'm not drawing any network. You can choose your own network. There is no restriction on that. The only restriction is in the fact that number of inputs will be equal to the number of outputs. Okay. Okay. What is unknown? Theta. S is known, I mean, in the sense that you will decide theta is unknown. How will you find out that? Fisher divergence. This is a vector. You see, we should use the formula that I just wrote, right? So my uh, so to find theta, what I'm going to do is I'm going to use the Fisher divergence, which is equal to. I'm going to use the original definition to start with. Exponential. You will draw data from p of x, and then there's a half outside. Sorry, and then you have your gradient of log of px x. Pxx you can write p data also. So if it is easy to follow that, that's p data minus s theta x, and then the norm of it. This is my original Fisher divergence by definition, right? This is the original Fisher divergence by definition, correct? So what have we done here? Think about it. Now when you are training it like this, and my network is a scored network, there is no concept of exponential of minus f theta, or exponential of f theta by z theta, whatever you want to call. Minus is can be there, cannot be there. That so you can imagine that this is not based on energy based model. You have a scored network. You do not have an energy model now. If it was an energy model, then what the output of that should have been a scalar, and that scalar you should have taken an exponential of that. And not only that, you should have also at least written the normalizing constant of that. All of that is now out of the picture. That does not exist here. And that does not exist. There is no normalizing constant because code is independent of normalizing constant. Code is a vector field. I mean, and because it's a vector gradient, so that normalizing constant vanishes. One of the advantage obviously is that all the business about Z is out of the picture now. The main idea of score based network is that you will start with a network that will take input X, the data, and give you score. It will not give you F, some energy or something like that. It will not give you PDF. It will not give you sample. That will give you score. This is the main difference from any of the network we've done earlier. In autoregressive, what did we do? Input was x1 and then just probability of x2 given x1. The network was giving me mean and standard deviation of that. Correct? VAE, same kind of thing. GAN, we're giving samples Z and we're getting samples of X. Normalizing flow, flow based model. In that case, it was an invertible network. We're giving Z, we're getting X samples. Then came energy based model. We're getting F, which was an energy functional kind of thing. Now here in score based model, we have the score coming into the picture, right? There is no mapping from sample to sample, Z to X. There is no mapping from x1 to x2 because that's what autoregressive was doing. And there is no predicting the parameters of uh, some neural network or some distribution, mu and sigma, like we did in VAE, right? The difference is clear. No, that so you will not do, no. So that we never use this form. We'll use the form that I wrote earlier. So that I'm going to write next. So what we'll use is not this form, right? This is equivalent to, we have already proven it last time for scalar and vector. I wrote it just now. We'll use the form that I wrote earlier, which is expectation x coming from Px, and then you have the score. So norm of the score okay, one bracket is missing, half of that plus diagonal of the gradient of s theta x, not diagonal, sorry, trace. Previously I wrote diagonal or trace. Trace, I wrote it correctly, right? Check if I wrote diagonal, that was wrong. It should be trace. I hope I wrote correctly. But trace. Okay. No. Hessian it was because that was log probability. Here it is already score. So one derivative goes down. That's why I wrote, actually wrote this one initially. When you corrected me, I actually directly wrote this one last time. When I said that, remind me, right? Okay, clear. And you can imagine that this relates to the energy based model, whatever you did earlier. You just replace s theta with grad of f theta, and it will come here, right? But this is much broader. So score based model is a superset of energy based model. Energy based model is a superset of autoregressive and flow based model. These models we are going one by one, but it's not like that they are distinct from one another. One model can be encompassed within the other model. So score based model is superset of energy based model. Energy based model is a special type of score based model. You can imagine that if you train using score, obviously, and then autoregressive and flow based models are a special type of energy based model, and so on and so forth. Right? Okay, so we're going to train with this. How will we train with this? Let us see. The same network I'm going to take. Okay, so I'm going back. Now to train this, what do we need? We need s theta of x. So s theta of x is easy, just a forward pass. I'll get s theta, take the norm of that. So from here, directly I will get s theta of x and norm of that. This is straightforward, no big deal, right? The difficulty, however, is, as was the case with energy based model, with the second term. For the second term, what will you do? You will do a back propagation. So you will do a back propagation. So BP, and back propagation will give you gradient of x s theta x. And once you have this, then it's simple. You just find out the trace. Now, obviously, we will not do the total back propagation. If you do the total back propagation with respect to x, the matrix might become very large. You do not want to compute that large a matrix. So what you will do is you will take S1, and from S1 you will backprop to find del S1 del X1. You will take S2, you will do a back propagation to find del S2 del X, del S2 del X2. You will take S3, you will do a third back propagation to find out del S3 del X3, and just sum them up. Which means instead of a complete back propagation, which will give you a huge matrix, you will do a back propagation, but one variable at a time and d times, in this case 3 times, and sum them up. it will reduce the cost, right? You are not dealing with that big a matrix, right? In some cases. Okay. But even after that, this is very expensive. So you should not do this. I mean, no one does this. Okay. We'll see how to handle this, but this is still expensive. But I have a question. Which one do you think is more expensive? Energy based model trained with score or score based model the way I score it now? And why? Correct. Energy because you have to do twice. So there is more number of back propagation that you will have to do. So energy based model will be more expensive. Even this is expensive. This does not scale that much. Uh, but energy based model, even with score matching, is more expensive because the number of derivatives you are taking is more. In this case, you are directly getting S. Why? Which is what is expensive? Because that matrix will be huge. You have to compute those. You have to imagine you are training it for 500 epoch, in which because of your batch size, each epoch it is getting updated 100 times. So 500 times 100 times it is getting updated. Now instead of now during update you have to take gradient with respect to theta. Along with that you are taking gradient with respect to x. This is not for making it a sparse matrix. You would have to run back propagation d number of times. If you calculate a full matrix, then you can run it once, but then that matrix is huge and storage constraints will come into picture. Because you have to keep in mind this gradient is only giving you the loss. You have to take gradient with respect to theta once more. So whatever we are doing, whatever gradient business we are doing is only to calculate the loss function, which is Fisher divergence in this case. You have to take gradient once more. Now, if you are relating it with, let's say, physics inform input is 1, 2, 3, 4. That's the maximum input you have. X, Y, Z, T. That's all. In this case, your input is 1000 cross 1000 pixel. No, you're again when you have X, Y, Z, there we are not talking about data point. I'm talking about input variable. Don't confuse data point with input variable. When it is X, Y, Z, T, those are the four variables. You have nothing else in physics informed neural network. Each might have millions of points. That does not matter. You have four inputs. In this case, your input is 1 million, 1000 cross 1000. So now imagine you would have to create a matrix of million cross million and then take the trace of it. This is one option. Trace is simple. Correct. But correct. Exactly. That's why I said OD. In that case, you have to do back propagation for each S once, which is OD, which is million number of million back propagation you have to do. Correct. You have to do million back. It's a very simple thing of doing for loop or Weissen's vector calculation. Classic programming problem. Whether you're using for loop or doing a vector calculation. That's all. So then, and remember this million back propagation you are doing per update. So that becomes very, very expensive, right? In that case. But it is still less expensive than energy based model. Because energy based model do one more round of that. So it's still very much less expensive than the energy based model. Clear? Any doubt? Okay. So this has problems, right? Because this has problems, uh, the next thing that was proposed, I mean, so basically, even before proposed, right? So what do we need? We need algorithms that can handle high dimensional problems, right? And there are two strategies for that. We'll talk about both. The first one is known as denoising score matching. Okay, and those who knows diffusion, you can imagine I'm going in that direction now. That is known as denoising score matching. Okay, the second one is known as uh, slicing score matching, or yeah, slicing. Although you do projection, but let's say slicing score matching. Okay. These are the two things that we're going to discuss next. But there is one thing that I'm skipping intentionally. Do you know what? How do you sample a score network? I don't have PDF. I don't have anything. We'll talk about that at the end. Okay. I'm talking about this core network. Till now, whatever we have discussed, the sampling was very obvious. Even in energy based model, you can imagine. I mean, I had at least had an unnormalized PDF. In this case, I do not have a PDF. I have derivative of the log PDF. So how do we sample? We'll come to that later. Okay, clear? So we need to do something about the computational cost. So how to reduce the computational cost? What is the reason of the computational cost? The grade, the the trace term, right? Somehow we need to eliminate that. Okay. So one algorithm that does that is denoising score matching. Okay. So we are going to talk about two, as I said. One is denoising score matching. The other one is uh, slice score matching or slicing score matching, whichever you like. Okay. Slicing is probably the correct term, but that doesn't matter. These are the two ways of doing that. Uh, Both will have. I mean, I personally like slice one more, but denoising is more popular. So we'll start with denoising. Okay. Denoising score matching. So what we will do is as follows. For either of this, we will first talk about the philosophy. There are some philosophical aspects. We'll talk about that. Then convert that philosophy into mathematics and see what is happening and why it is simple. Okay. Okay. So first we are talking about denoising score matching. The philosophy is as follows. Instead of matching with the exact probability or log probability, gradient of log probability, right? We will match with a noisy version of the log probability. So if you have images from a P of x, we'll add small noise to each of those images. So if we add small noise, that is now not from the same distribution, that is from some other distribution. This distribution is what we will try to match with the score matching. So the philosophy is why we are doing it will come later, but the big idea is that instead of matching P of x or grad x of log of P of x, that is what it is, right? Grad x of log of P of x, right? Instead of using that, because that is the term that is giving rise to this uh, gradient of s theta. Okay, that term has a role in this grad of s theta coming into picture, right? Uh, Instead of matching with that grad of log of px, we will match with some, I mean, we will some q of x tilde, where q of x tilde is some noisy version of samples you get from p of x, which means we are bringing the concept of noising. I'll take the sample and add a small noise to it, and then that small noise we will work with that. We are also bringing the concept of transition probability. What we are doing is as follows. See, so I have, let's say, some image, right? some flow field, some dog, some cat, whatever is more closer to you, I have something like that. Okay. And this is a sample uh, X, let's call it, and this is representing, or this is a sample from Px. Okay. What you do is as follows: you take it, add noise. This is some noise that you are adding, some small noise, and once you add noise, you will get X tilde. Okay. So this, I mean, there will be something like Qx tilde given X, and you will have Q of X tilde. Remember, there is no one-on-one correspondence between the left and right. The first one has the correspondence, but Qx tilde given X is like adding noise. That is not the noise. Okay. And once you add the noise, what you get is Q of X tilde. You get samples from Q of X tilde. Okay. So what we do, as I said, the philosophy is work with noisy samples, which means mathematically what X tilde is equal to X plus epsilon, where epsilon is from some Gaussian 0 comma sigma square, which is a small variance, which is a hyperparameter, and where X is a sample from Px of X. You can write P data of X, does not matter. Uh, Q of X tilde given X, what will be the distribution? Gaussian. X tilde given X as the mean and sigma square as the variance. And what will be Q of X tilde? This you should be able to tell. What will it be? How will you find it out rather than what it will be? Exactly. Find out joint probability, marginalize. This is equal to integration Q X tilde given X P X X D. Not difficult, right? The only thing that is uh, little off is that we are now matching with respect to Qx tilde instead of Px. We are working with some noisy version. Yeah. P of X is not known, but you have samples of Px of X. Qx tilde is also not known. You don't marginalize, you write the formula. But you have sample, right? You can add small noise to it, and that's all you do. Basically, you create noisy samples. You take the clean samples, create noisy samples. Right? That's all you do. Okay? Correct. But explain is some small noise. Again, small x is what? Correct. You have sample, you know. You have training sample. Training sample. You have training sample, right? You know. You don't know the P of x, but small x you have samples. You have n number of samples. Each sample you take and add a noise. That you can easily do. You don't need to know Px of x. Obvi- Obviously. Obviously. I mean, x has to be known. Otherwise, how will you learn the distribution if you don't have any data? How can you learn a distribution with no data? And what does that even mean? X is a sample. Each training data is a random variable. That is the first philosophy of generative model. Generative model starts from the fact whatever data we have is some sample from some unknown distribution, and we want to learn the distribution. So X is a sample, but that is your training data, one of the training data. You are not for that sample. For that sample, it's a conditional distribution. When you take a conditional sample, it is for that sample and that's fixed. If X changes, mean changes. Okay. Any question here? Q X tilde given X, it will be right because you are conditioning on X. That means X is fixed. Whatever is the variance that will come, right? The linear regression. Okay. Reason you will get later. Yeah. I mean, not the reason. Your question should be: I'm making something noisy. How is it supposed to work? That is the thing. Correct. Not necessarily. Not necessarily. Okay. So why are you doing it will come later. Obviously, one reason I have already told you to make calculation simple. The question that I think is bugging all of you, and it should bug all of you, is that I have correct data. Why the hell should I make correct data noisy and use that noise data? Right? There are two answers to that. One is even if you're working with noise data, you will get the correct data. You will see that in a short while. That the loss function will make you learn the correct thing only. That is one reason. The other reason is that noise acts as some kind of regularization or smoothing. You can not smoothing, some regularization. You can think of it like that. Not exactly regularization, but you will see that soon. And most importantly, this will make it scalable. This will work with this. Okay. How? Wait for 10 minutes. Okay. So I'll repeat. The philosophy is that we will not work with the actual data, will make noisy. And then noisy data is from some noisy distribution, we will work with the noisy distribution or score match. Okay. That is the philosophy for now. How it will work, what will the score represent, what is the optimal scenario will come later. Okay. So now I have my score network, right? Score network, what will be the input to the my score network now? It will not be X, it will be X tilde. So as I had made my noise data noisy, input to the score network will also be this noisy data. Okay. Now what is unknown? Theta. I want to find out theta. I will use Fisher divergence as follows. So with Q tilde X, not Q tilde, sorry, Q of X tilde. With Q of X tilde as target, we write the Fisher divergence as follows. Okay. So f of theta, tell me how will it look? Expectation with respect to X tilde from Q of X tilde, and then inside the bracket, not the easy form, the original form of Fisher divergence. But how will it look? The original form of Fisher divergence. Gradient with respect to X tilde of Q log of Qx tilde minus S theta X tilde It is log, by the way. I forgot to write the log. I overwrote. Okay. And now we will do some algebra on this to reduce it and see if we can get something simple. Okay. We will work with this expression on the right and try to simplify it. So let us write it down and all of you will help me. Your job is to, yeah, help me. So let's see. Uh, Simplifying or opening the bracket, whatever. We'll do the exact same step that we did last time. When it was a square, what did you do? A minus b square, we wrote a square plus b square minus 2ab, right? Same thing we'll do. Okay, there is one mistake here. Half is missing. This half is not important, so I keep on forgetting it. I mean, how does it matter? But the original formula has it, so I should write it. Okay. So f of theta. Inside there is a norm, right? That is like a square. If I open it, what will I get? Half. Exponents, sorry, expectation I'll keep as it is for now. X tilde. Tell me, what will be the first term there? Norm of log of gradient, log probably, right? Gradient. What is the role of this term? To become a constant and vanish, not a function of theta. That's the role of this term. No role. Second term, norm of theta. Okay. Minus. What is the role of this term? To stay as it is. This term was never a problem for us. This term was existing even before. The only change is that x, instead of x, it has become x tilde. So the last term, tell me, twice gradient of x tilde log q x tilde transpose of the whole thing multiplied by s theta x tilde. Okay. Everyone follows? First term is not a function of theta. That's a constant for us. So we will ignore that term. Second term will remain as it is. Our main bottleneck is the green term. So we will now work only on the green term because it is the green term that was giving rise to that Hessian, right? And you can see that as, I mean, it is still there in some sense, but we will only work with the green term, but not only with the green term along with the expectation, because the expectation is additive, it will go inside, right? It will be expectation of the first term plus expectation of the second term minus expectation of the third term. We will only work with the expectation of the third term. Clear? So we will only focus on that. So we focus on the green term. Because it is a green term, let's call it G. Okay. So what is G? G is equal to expectation. There is a half outside, so I'll write that. Uh, Expectation. So the negative sign I'm keeping it there. Keep that in mind. When you substitute, the negative sign should be there. Expectation x tilde from q of x tilde twice gradient x tilde of log of Px x, no, q, right? Q. Okay. Q of log of Q of, again, please leave. Uh, Log of Q x tilde, right? Transpose, then S theta x tilde. By the way, one of you have to take attendance today. Suryansh is not there. This is the term, right? I hope I'm not missing anything. Yes, I'm not missing anything. The transpose is what I tend to miss, so I think I'm not missing that. If I miss the transpose, let me know. Okay. Okay. Clear? Now, what we will do is simple. 2.5 will cancel out, so I'm removing that. It is integration Q of x tilde. What is this term? Like last time, this term will do the same thing. What will it give me? Last time, remember we did it? 1 by q of x tilde multiplied by gradient of q of x tilde. I mean log, right? This will give you gradient of x tilde q of x tilde, okay, transpose s theta x tilde d of x tilde. Okay, simple. This cancels out. What we have is gradient of x tilde q of x tilde transpose s theta x tilde dx. Okay, nothing new. And this is exactly what we did last time. And just the transpose is the new thing. I mean, apart from that, there is nothing new, right? What is q of x tilde? Huh? Q of x tilde is noise distribution. Mathematically, what is q of x tilde? We are doing mathematics now, not intuition, right? What is q of x tilde? We wrote it. This, the marginal distribution we wrote, right? Let us substitute that. Okay. So we substitute that, so which implies g is equal to, there is one integration, grad of x tilde stays, right? And then there is another integration coming into picture, q of x tilde given x multiplied by px x dx transpose s theta x tilde dx tilde, right? Now gradient is a linear operator, right? It will go inside the integral. If it goes into inside the integral, what will I get? So integration to integration actually, and then gradient with respect to x tilde, uh, q x tilde given x, pxx transpose, and I can just write transpose here now actually, s theta x tilde dx dx tilde, right? Now I want your help. What is this equal to except a transpose? And I will give you a clue. We arrived at gradient of the PDF previously from a term. So here we will do the reverse of that. So what was the term from where we arrived at gradient of x of p or q? Gradient of log of q multiplied by q. So I can do the same thing here. So see if it is making sense. This I am saying is equal to q of x tilde given x, right? And then gradient of x tilde log of q x tilde given x, right? You can get the same term. But we were going in the opposite direction. I mean, or the correct direction till now. Now we are going in the opposite direction. And there is a very good reason we are doing this. We are doing this because we want to represent everything in terms of expectation. And expectation with respect to x tilde given x. Why x tilde given x? Because that is Gaussian, I know. So that gradient will not be a problem. That will be a Gaussian gradient. The Hessian will be out of the picture. Now look at where the gradient is. On a term that is Gaussian, log of Gaussian. So that means I will get x minus x tilde by sigma. That's what I'm going to get. So that gradient calculation and the diagonalization is now out of the picture with this. Okay. So that was the whole business. So you ask now why Gaussian? This is why the Gaussian. Because it need not be Gaussian. It should be some noise which I can take derivative easily. And Gaussian happens to be one of, I mean, a noise for which I can take derivative of the log of that easily. I mean, you can take exponential. There is no problem with that. Gaussian is taken because Gaussian has other properties also. And Gaussian can, I mean, noise with exponential is non-negative. That means you are saying that noise is only, that does not work, right? Okay, so finally, this is equal to uh, maybe I should write the total term together. I'm doing one step jump. Just let me know if you're not able to follow. I'll write it. Okay, but let's see. So x drawn from pxx, x tilde drawn from q of x tilde given x, which is a Gaussian, and then what is there? Gradient of x tilde q x tilde given x, transpose of that multiplied by s theta log, right? Thank you. So log I'm writing like this. I don't want to delete it. Log of q, right? I mean, maybe I should delete it. I don't like. Let me delete and write it. log of q. Everyone follows? Simple, right? Huh? Raid I wrote without the transpose, so that's why I did not write. I mean, the transpose is obviously there, so I was trying to mark without the transpose part. So that's why I did not. Clear? Now, this is only one, the green term. There are additional terms there. Where is that? I need to put a come and substitute it here. So what is my loss now? So therefore, f theta is equal to, first term was constant, right? Plus the second term was half expectation x from px norm of s theta x tilde, something like this, right? Huh? Correct, 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 correct. Thank you. Correct. Thank you. X tilde is simple, q I have to delete. X tilde, I can make the same thing as x tilde, right? X tilde you are sampling from, right? Okay. This is okay. Minus uh, the term is, the half has cancelled out, so maybe I should put the half back. Exponential, sorry, expectation of x from px, x tilde from q, uh, x tilde given x, and then what do I have? Gradient of x tilde log q x tilde given x transpose s theta x tilde, right? Okay. Lastly, almost lastly, 2 3 more sentences. Yeah, almost lastly. Let me know. Can I not write this expectation as follows? This expectation is it not equal to the same expectation that I wrote earlier? Is this expectation not same as this? Same, right? Because how do you get x tilde? Sampling from x tilde means you will sample x, which is a training data. Condition on that, you add a noise to that, you get x tilde. That's exactly what we're doing here, right? This expectation is actually that expectation. They are same. And if they are same, the two expectations can now be combined into a single expectation. We combine them. This is equal to half expectation x from px x tilde from q of x tilde given x. This term remains. Now, What do we have inside? Norm of S theta, then minus 2 times norm of S theta plus some term, I mean multiplied by some term. If I add one more term, can I not make it a square? I can see a square minus 2ab. I just need to add a b square and subtract a b square. That will give me a minus b whole square, and then other b square will go away. We'll do that. I have a square minus 2ab. I'll add the b square and I'll subtract it. That subtraction I'll take separately. Agreed? So, first term is s theta x tilde. This is your a square. Now the 2 was sitting outside. I have brought it inside, minus 2, but that is b square anyway. S theta log of q x tilde given x transpose s theta. This is your 2ab, s theta of x tilde. What is your a square or b square, whatever you take a? What is the other term? Correct. Norm of that, right? Plus norm of grad of x tilde log q x tilde given x, and then that is the extra term I am giving. So to subtract that also, to minus the same thing. Okay. Now the last term, the expectation I will write separately. The other terms will form the square term. So let us write that term. So a square minus 2ab plus b square I have. I will write that in form of a norm, different norm of the difference. The last term I will separate it out. So what do I get? Remember the constant I have already removed. So I mean, maybe I should write the constant also. Okay. This is equal to then constant plus expectation x from px, x tilde from q, x tilde given x, and then norm of gradient of x tilde q, x tilde given x minus s theta x tilde log again. Log, I keep on forgetting. Log of q x tilde given x, right? Plus or minus. What is the term I have? Minus half of expectation of. Is there any theta? That is a another constant, plus constant. So that term is not useful to us, right? Yes. Thank you. Okay. So clearly my loss function will now only be the middle term. The first constant does not matter, the last constant does not matter. Only the middle term will be my loss function, right? And this loss function looks reasonable. Why does it look reasonable? That gradient you can compute, because that's a Gaussian, at least in our example. S theta anyways we are getting. There is no Hessian, there is no trace, there is no Laplacian, there is no Jacobian. All of that is now gone out of the picture. But there are two questions. One, does it really work? Because we started with a wrong matching, right? We changed our target, we changed our goalpost. Does it really work? First. Second, why is it called denoising? We only added noise. Where is denoising here? There are two questions, right? Why is it called denoising? And does it really work? I changed my goalpost. Is that okay? Let us see. Right? First, does it really work? Second, why is it called denoising? So let us take the second question first, right? Because that will answer the first question. So I'll do very simple thing, and you will do it for me. I want to put the exact value of grad of x tilde log because we know that is Gaussian. So we know we'll take the Gaussian and compute that gradient and put it there. So substituting qx tilde by x is equal to 1 by sigma root 2 pi exponential of minus 1 by 2 sigma square. Uh, Again, I am taking a scalar. You can take it a vector. Nothing will change. Okay, you can take it a vector also. That's okay. Uh, X tilde minus x whole square. Okay, and if you take it as a vector, you know it will be x tilde minus x transpose small sigma times I inverse. So that is sigma inverse, whatever sigma square inverse multiplied by x tilde minus x. That's what you will get, right? Okay. So if I substitute it, what will I get? F theta, I mean, is equal to constant plus half expectation x belongs to px, x tilde belongs to q of x tilde given x, and what do we have inside? Norm of what? X minus x minus, I mean, x minus x tilde, because there is a negative sign. So if I take, yes, x minus x tilde by sigma minus s theta of x tilde, not sigma square. Uh, Sigma will means if I take sigma square, yes, sigma square, correct. Yes, okay. 2 that will come outside, this will cancel, yes, sigma square. That doesn't matter to very honest, but yes, sigma square. Okay. This is what you are getting norm, obviously. I mean, so, so now we are training for this loss function, right? What do you think when you train for this loss function, theta will try to do? What is the optimal S theta? In optimal S theta, what will it match? It will match x minus x tilde by sigma square. What is x minus x tilde? Noise. What is S theta learning? The noise that you added. What it is trying to do? Denoise. Basically, what it is doing is that you got that x tilde by adding this noise. Core network is now trying to learn that noise so that you can denoise it and get the original sample. Think about it. S theta, what is it trying to learn? How much noise you have added. And if you know that noise, S theta will also help you denoise it. You you know the noise distribution, but S theta is, you don't know the noise that was added to each image. That you don't know, right? You don't know, I mean, during inference, you will start with a noise, and that time you will not know what that noise is supposed to be. It is learning how to denoise. That's why we call it denoising core matching. And later you will see that if we do it multiple number of times, that will become diffusion. Diffusion is exactly this, you do it multiple number of times. You don't add noise once, you add noise multiple number of times, and then repeat it. That's what denoising diffusion model is. You just extend it. This was proposed by, I forgot who, I think Vincent or someone, but in 2011. Denoising diffusion model came later, but that was just an extension of this. Yesterday is giving you backward pass. It is taking noise and giving you how to remove the noise. That is not useful because during generation you will not generate the same data that you had. During generation, it is supposed to generate some new data. For that new data, you did not add noise to get that data. So what will you subtract? That is known. Will it predict it? Why will you predict how much noise we are adding? I know that. You cannot remove it. You cannot. Because during inference, you are starting from some noise. That noise is different from the noise you will get when you take an image and add noise. Both are from the same distribution, but there's different samples of that. So how do you know for that what is that thing that is to be denoised? What is to be denoised has to be function of the noisy thing. Otherwise, you will never be able to generate new samples. Obviously, that you can ask that, but how do you generate sample? Yeah, I have not yet discussed. That we'll discuss. But the goal is to just generate sample, right? I have not yet discussed how to generate sample. So you can always say that. Yeah, correct. Left hand side is noise. You agree, right? No, no, no. S theta is taking not a noise. It is taking a noise Z image. Noise is x minus x tilde. X tilde is not noise. X tilde is the noise. I mean, X tilde is the noisy image, right? You follow? Okay. So if that is the case, now you think, what is S theta learning here? In the optimal case, it should be the inside term should be equal to 0. In the optimal case, it's a mean square loss, right? It should be equal to 0. The norm has the minimum of norm is 0. When will the norm be 0? For any x tilde, S of x tilde is equal to x minus x tilde by sigma square. What does it mean? It means in the optimal case, it is learning how much noise did you add. It is not removing it. Removing is your job. It will come in this inference or generation part. But it is learning how much noise you add. It is giving you a tool that will allow you to denoise at least. Now, right now it is not doing. It is learning the noise, right? Okay, clear? So this is denoising core matching, right? Yeah. This is only one of the method. There is one more method I said, so let us, but that will not take time, which is the slicing score matching. So the other one is, so this and the sampling will be very fast. Sampling actually you already know. You are just not able to recognize. That's all. Uh, Slicing score matching. The idea of score matching is you want to match the score of your data or you want to match the score of the target distribution, which is the data distribution, and the score of your network. In score matching, you want to match score of what you are predicting and score what your target distribution has. Hmm. Yes, yes. I mean, it is predicting score is coming out to be the noise. Yes, correct, correct. It does not work. Yeah, because it varies, so sigma should be as small as possible. Yes, because sigma cannot be too big because then the target will become very small. Sigma cannot be too small because that will go to infinite. Sigma square is sitting in the denominator, right? It has to be somewhere reasonable. It is small but small enough that you can work with. Yes. Okay. So slicing score matching. In slicing score matching, the idea is that, or rather, the question I ask is, how do you match score? Score is a vector field. If you have score, you will try to match each of those vector fields, and if they match, that means the score is matching, right? Can you tell me any way of matching two vectors? It's a vector field. How do you match two vectors? Some easy way of matching two vectors. Determinant. It is expensive. No. Dot product is very close. Dot product gives you what? Yes, but that remember that this is high dimensional. I want to reduce the dimension. In that sense, the problem is that we don't want that high dimension, right? Projection. If two vector fields are same, no matter what random projection you do, for the same projection, they should match. And that, I mean, no matter, right? But projection allows you to reduce the dimension. The vector field which is high dimension, you take a random axis or whatever, project onto that and match it there. This random thing can change. And as a result, if it matches for all those random axes, that means the vector fields are matching. This is the idea of slicing score matching, where you project it into a random axis and match it there. Dot product of two things you cannot do. Remember, keep that in mind. Be- yes, but if we could do that, we would have done that. But we cannot do that. Why? Because you don't know the score of the distribution to start with. You don't know the score to start with, right? So slicing score matching. The idea is project onto a random axis. So it is like 1D and match, right? So what do you think the loss will look like with this? F of theta or whatever, L of theta. It will look like what? You will draw samples, right? From the training. So that one expectation will remain on the sample. The other one will be on which axis you are projecting to. So there will be a 1 by 2 anyways. So I was expectation, let's say V from Q of V. This is kind of random. You can decide what you are generating randomly. X from P of X. Now no X tilde, X original. And then inside, what is the norm you take? Norm of first was gradient of log probability. You will project it on V. So V transpose gradient of uh, log Px, right? And minus 4 also you will project. So V transpose S theta x square. Square, not norm, because you projected it onto one axis, so it becomes scalar. It becomes a scalar because you projected it onto one axis. So this is the slicing score matching. Obviously, will not work with this form log of px. You don't know. That's what I was saying. We'll simplify it. We'll simplify it using the exact same thing we did earlier, which means you will simplify it using integration by parts. And tell me, what will you get if you simplify it? Can you tell me without doing anything? The expectation will remain as it is. Now inside, what are the terms you get? Half. What are the terms you get? V transpose S theta. I think square of that or something like that you will get. Plus half and half 2 will cancel out. V transpose gradient of x, sorry, yeah, gradient of x S theta x V. Not making sense? Hmm? Not making sense? Let us see. Let us go back, 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 go back. Look into this expression. There was gradient of x square f theta x. Gradient of x f theta is s theta, right? And that term had gradient of x f theta, square of that. That will become s theta, right? But now s theta is not alone. Along with s theta, there is a v transpose sitting there. The first term will become v transpose of s theta whole square, correct? And the second term, how did you get the second term? You remember? It was 2ab term that gave me, right? Because of that, v transpose and v will come and this term will remain. Okay. I'm not deriving it, but it is very simple to derive. Just keep in mind that the second term came from 2ab. A and B both have v transpose. So that's why 2n v transpose and v will sit. The first term came from s theta. So that will become v transpose s theta. That's all that is changing, nothing else. Now, why is it easy to compute? It is easy to compute because you can now compute all of this using a single backward pass. One backward pass is all you need for computing the second term. First term is easy. The second term is the challenge, right? Second term, what will you do? See, you have x, you have a network, it gives you s, right? So, just to write it properly, you have x1, you have x1, x2, x3, the same thing, right? You have s1, s2, s3. V you sample randomly, there is nothing to learn with V, right? So you will do a projection using V and you will get uh, what? S times V, S transpose V or whatever, or V transpose S, whatever you like, correct? You will get S transpose V. Take this and do a back propagation. What will you get? Only S is function of X, V is not a function of X. So you will get grad That's what you will get. One vector multiplication you will get this, which is a vector by the way, matrix vector multiplication. So you don't have that storage thing issue now. You will multiply it with a V transpose, which means you can now compute this whole thing, this second term, using a single backward pass. Obviously, for training you need additional backward pass, but OD has now become 1. And it is happening because of the way you are computing. If you compute S theta completely and then take gradient, then you are in the same position. But we don't do that. What you do is that we proceed in a way where it's a matrix vector operation, you will proceed in that sequence. And when you proceed in that sequence, the memory reduces. Yes, yes, yes. No, no, that is random sample, right? Random. And that will change every epoch or every time, every with each batch that V will change. Clear? We'll repeat once more. I went little fast here, I know. So what we are doing is very simple. We are saying that our problem is the dimension. Our problem is the dimension. So let us do one thing. Instead of matching the vector field, which is high dimensional, 1,000,000 dimension, right? We'll project it onto a single plane or single axis and match it there. That reduces the dimension. And this axis will keep changing for each batch, which is like matching in all the axes, right? Now, when you do that, our high dimensional thing is now compressed into a single number, scalar. And that we are doing with that V now coming into picture. With that V, we do some, I mean, the same derivation, and that becomes something like this. And our main bottleneck was always the second term. It still is. But because V is there in form of vector, we do not compute grad S, grad X. We compute grad S, X, grad SV. And SV is a scalar. So grad S, grad SV is a vector of low dimension. And that's what you do. So basically, you will never compute it grad of S, basically, what I'm trying to say. This you directly do not compute. What you compute is grad of X, Sxv. This is what you compute. It becomes a scalar, right? I mean, the output is scalar. S transpose V is scalar, right? Correct. So, and now we will do one backward pass. S is not a matrix. S is a vector. S is S1, S2, S3, right? So it's a vector. Okay. Any question? I think because of this different axis training is unstable. I don't know. I've never used it, to be very honest. Because remember that each time you're projecting into a different axis and trying to match. Ideally, you should match in all axes together. Matching in one axis at a time is probably unstable, is my guess. I don't know. Okay. Correct. So we are not matching in one axis. We are taking expectation with respect to all the axes, right? I mean, so that V is keeping on changing. The axis where you are projecting, that projection matrix is changing. Yes. Yes, it loses information, but for a single update, right? For the next update, it is now in another thing. So combining it might have all the information, but it is the optimizer is not getting all the information together. I mean, for each update, it is only using a part of that information. That's why it is slicing, right? The information. That's why it is called slicing format. Okay, last thing, and it will be done by this slide, okay? Because you know already. How do you, what is the best way, at least based on what we have covered, to sample from a energy based model? How do you sample from energy based model? MCMC? Which MCMC? Metropolis testing, but that is not that good. What is the better one? Langevin. Langevin, right? Tell me, what does Langevin look like? Langevin x t plus 1 is equal to xt plus eta times grad of x of log of p x x plus square root of 2 eta epsilon, where epsilon is from Gaussian 0 comma 1. This is the Langevin, right? What is the second term? Grad of x of what is that? That is the score. If I know the score, I know how to sample from it. For sampling, I do not need the distribution. I need the score only. The score has the information of the distribution. If you integrate the score, you will get the distribution up to a normalizing constant, and that constant can be found out by enforcing that it will be equal to 1. So when you are sampling, even in Langevin, unadjusted Langevin, right? We were using score, but that time I had not introduced score. We were telling that log probability gradient, the mode it will approach, and all of those things. But is that not score? What score does? So basically, once you know the score, you will just substitute the score here. Using your score network, you can now sample, right? And you will obviously have to sample in multiple steps. You will start from some initial condition, and the chain will go. You will throw the burn-in, whatever it is, right? And then you will get some sample, and that's all. I don't know. Yeah, it obviously came earlier, but whether from here they got inspired or not is not very sure. Obviously, there has to be some inspiration from there, but it is not very obvious that whether they got inspired from here directly or not. There has to be, because why score? Why not s theta square? I mean, I can come up with other metric also. So there has to be some, because my guess is that score was proposed by Stein long back, not in the context of deep learning or something. So someone observed that these two things were separate, they brought it together. Okay. So this is your score based model that we discussed about how to sample from it and all of those things. This is also the beginning of diffusion, denoising diffusion model, right? And we'll see what mode is there in denoising diffusion model, but this is obviously the starting point, right? Okay, thank you.